So we have been given In is equal to integral 0 to 1 x to the power of n times tan inverse of x dx, where n is a natural number. So such type of questions fall under the chapter reduction formula in the definite integral chapter. So let us consider In equals to integral 0 to 1 x to the power of n times tan inverse of x dx. So as I said, this comes under reduction formula. So in majority of the reduction formula problems, we make use of the method of integration by parts. So if we choose my two functions judiciously, then we can solve such questions very easily. So here I am taking tan inverse x as a function to be differentiated and x to the power of n as a function to be integrated. So I'll perform integration by parts. So first I'll integrate x to the power of n. So that gives me x to the power of n plus 1 over n plus 1 times tan inverse of x. We put the limit from 0 to 1 minus integral of, then we'll integrate x to the power of n. So that will give me 1 over n plus 1 times x to the power of n plus 1. I have pulled out n plus 1 common out of the integral sign. And then we'll differentiate tan inverse x. That will give me 1 upon 1 plus x square. Now let me denote the second integral that I've got after integration by parts by I1. So I'll again apply integration by parts on I1. So we write I1 is equal to integral 0 to 1 x to the power of n plus 1 over 1 plus x square dx. Then we'll do a small manipulation with this. So we'll pull out x square common from here. So that will give me x to the power of n minus 1. And then we'll add and subtract 1. So that way what will happen? Whatever is in the denominator, that will be developed in the numerator too. And once we do this splitting, so we'll have one integral as x to the power of n minus 1 dx 0 to 1 minus integral of 0 to 1 x to the power of n minus 1 over 1 plus x square. Now the original integral that we had tan inverse x in it. So once again I'll apply integration by parts on this step or on this integral. So let me denote this integral by the symbol I2, and I'll take the numerator function x to the power n minus 1 as the function to be differentiated and 1 over 1 plus x square as the function to be integrated. So as you can see, I have denoted it by I2. So we'll again apply integration by parts. So x to the power n minus 1 is kept as constant, and we integrate 1 over 1 plus x square to get tan inverse x. We put the limits from 0 to 1. Then we differentiate x to the power of n minus 1. So 1 n minus 1 comes out of the integral sign, and we have 0 to 1 x to the power of n minus 2 tan inverse x dx. So as you can see, this has now become In minus 2. So in the formula for In, if you replace n by n minus 2, you will get this In minus 2. So we'll just perform this substitution. So we'll have I2 equals to, let me put the limits. So the first integral will simply become pi by 4, and my second one will become n minus 1 and In minus 2. Now this value of In minus 2 I'll take and I'll substitute where I have labeled I2 over here. So once I have done all that substitution and we'll simplify, so we will get I1 is equal to x to the power of n by n, limit from 0 to 1. So we have performed this integration which we had left earlier, minus I2, which simplifies to 1 over n minus pi by 4 plus n minus 1 plus n minus 1 times In minus 2. So we'll take all these values and we'll substitute them in the given expression, like which was initially what we called as I1. So let me just clear some of the workings over here. So I have again denoted what is I2. So this is what I got as I2, and I'll take. So we get In is equal to pi by 4 n plus 1 minus 1 over n plus 1 times 1 by n minus pi by 4 plus n minus 1 times In minus 2. Then we multiplied throughout by n plus 1. So I have already done that. So that way we get n plus 1 In minus n minus 1 In minus 2 equals to pi by 4, and pi by 4 will get added up to give me pi by 2 minus 1 by n. So my answer will become B.